Hello guys, welcome to our channel. One of the fundamental building blocks of calculus is the concept of the derivative of a function. We will attempt to comprehend this concept through an unusual method of learning mathematics, namely through common errors that people make. Typically, when learning a mathematical concept, we are given examples of that concept. It is, however, equally as effective, if not more, to learn cases that appear to be similar to what we are learning but are not. The advantage of learning this false positive is that it makes it easier for us to detect mathematical anomalies. In a sense, our mathematical bullshit detectors becomes more sophisticated. If we try to draw an analogy to the sciences that deal with the real world, we have an intuition of what is physically possible and what is not. However, in the realm of abstract concepts, we lack this intuition of the physical world. If you stick with us till the very end, we promise to make your mathematical intuition stronger. You will learn how to identify two very common mistakes that students make while mindlessly applying derivative formulas. So that was enough philosophy. Now let's see some math magic. Some of us have seen logic-defined computations proving 1 equals to 2, haven't we? The simplest ones are based on a very common mathematical error that students make while learning algebra for the first time. It is known as division by zero. Let us look at the computation in action and try to spot the error as we go. Let us now assume that a equals b. Then multiplying both sides by a results in a square equals ab. Subtracting b square from both sides yields a square minus b square equals ab minus b square. Factoring both sides, we get a plus b times a minus b equals b times a minus b. Because we assumed a equals b at the beginning, replacing a with b in the left hand side gives us 2b times a minus b equals b times a minus b. Cancelling a minus b from both sides, we have 2b equals b for all b. That is 2 equals 1, which is simply not true. If you miss the step with the error and you want to find it on your own, you may pause the video at this point and try to spot it. As previously discussed, there is a division by zero error at step 5. We began with the assumption that a equals b, which implies a minus b is equals 0. Therefore, dividing both sides by a minus b would result in a division by zero error. That was the teaser act of this magic show. Now is the time for some real math magic. Are you watching closely? Multiplication can be thought of as repeated addition. That is, a times b equals a plus a plus a repeated b times. 2 squared is equals to 2 plus 2. 3 squared equals 3 plus 3. In general, x squared is x plus x plus x repeated x times for all non-negative real x. At this point, we will need a bit of high school calculus. Don't worry if you have not learned it or you are a bit rusty, we will use just one result. The derivative of a polynomial x to the n, that is d dx of x to the n, is given by n x to the n minus 1. Now let us consider equation 1 once more. Using the polynomial derivative formula, we have 2x equals d dx of x plus d dx of x repeated x times. Therefore, 2x equals 1 plus 1 plus 1 repeated x times for all non-zero x. This implies 2x equals x or 1 equals to 2, which is simply not true. Curious viewers may pause the video at this point and try to think about the problem on their own. For your convenience, we will leave all the formulas and calculations on the screen. Now that you have looked at the paradoxical statement thoroughly, and some of you may even have come up with their own explanations, let us look at a way this can be explained. We stated in equation 1 that x squared equals x plus x plus x repeated x times for all x. Let us now substitute 1.1 for x. So 1.1 squared equals 1.1 plus 1.1 repeated 1.1 times. Repeating something 1.1 times doesn't really make sense, does it? Only numbers like 1, 2, 3, so on up to infinity
makes sense in this context. These numbers are called natural numbers. With this in mind, if we plot the left hand side, it looks something like this. However, if we plot the right hand side, it looks something like that. One way to think about derivatives is to think of them as tangents to a function. So, how do we find the tangent to the right hand side, that is x squared at say x equals to 2? We take a small step towards the right from the point x equals to 2, draw a vertical line at this point and mark the point where it intersects the right hand side. Then draw a line from the original point and the point we just marked. Note that this line crosses our function twice in the neighborhood of x equals to 2. If we keep repeating this process with smaller and smaller steps to the right, the line we draw each time will be closer and closer to the actual tangent, which is the line that touches the function at just one point x equals to 2. This process of taking smaller and smaller steps to approach an ideal condition is called taking the limit. And the process of taking the limit of the chords joining the points to the right is referred to as derivative by first principle. But if we try to do this to the right hand side, we see the problem immediately. The smallest distance that we can move to the right of the point x equals to 2 is 1 to the point x equals to 3. We cannot move smaller than that because, as we discussed before, this function is only defined on natural numbers. As a result, we cannot take the limit in this case, and the derivative at x equals to 2 is not defined. In reality, the derivative is not uniquely defined for any x, including natural numbers. This is the first mistake that we promised in the beginning, applying derivative formulas to functions that are not really differentiable. How about we look at the anomaly that we were discussing from an algebraic perspective? Suppose we replace the second x in this expression with fx, a generic function of x. This makes it more general and helps us distinguish between the two terms of the multiplication. If we expand the multiplication as we did before, then x times fx equals fx plus fx plus fx repeated x times. Why not also put the derivatives as we did before? Now, what does the left hand side of the equation say? Multiply x with fx, then take the derivative with respect to x. But if you look closely to the right hand side, you will notice that we have switched the order of the operation. We first take the derivatives of each term, then sum them together, which is the same as multiplication by x. This is also a common source of error for students. We tend to switch the order of mathematical operation and expect the same result, which is not always the case. Now that we understand the qualitative nature of the anomaly, how about we try to quantify it? Let us take the derivative of the left hand side using the product rule of derivatives. This gives us d dx of x fx equals x d dx of fx plus fx d dx of x, which equals x d dx of fx plus fx. We will call this equation 3. If we take the derivatives on the right hand side, then d dx of fx plus fx repeated x times equals x d dx of fx, which we call equation 4. If we compare equation 3 with equation 4, we see that in the second case we are missing the term fx. What have we not accounted for in equation 4, aka the left hand side? Let us look at it more closely, shall we? Are the number of terms on the right hand side dependent on x or not? Clearly, the number of terms depend on the value of x, but while differentiating, we did not differentiate the number of terms on the right, which is a function of x. Perhaps a simpler case will illustrate this better. X equals 1 plus 1 plus 1 repeated x times. The right hand side is obviously not constant. The number of ones is dependent on the value of x. Now, looking back at equation 3 and 4, we can understand that differentiating the number of terms gives us the extra factor of fx. This is the second major thing students tend to overlook, not accounting for all functions of x when calculating a derivative. Dear viewer, this was the end of this video.
We hope that we made it interesting enough for you to watch, and as a result, you have learned something. Our endeavor has been to make people interested in math, so that more people take up math as a career, and also to encourage people in other fields to view math as a powerful extension to human intuition and not simply as something that you need to pass exams. Disclaimer: most of the explanations are credited to questions on Stackexchange. The links are in the description, check them out and have fun exploring math. Ciao!